clicker. Okay, so I'll start off with the man behind the project, Chris Latner. Let's give a face to Chris. This is how Chris looks like. He is currently 37 years old. He graduated from University of Portland with a bachelor's in science. Then moved over to University of Illinois. Graduated there with a master's in computer science. As part of his work at the university, he had a research project which sort of later evolved into LLVM. And he was one of the two main researchers assigned to that project. And sort of this is a good example of your work in the university you're currently studying at, whether it's a bachelor's program or a master's, could evolve into something really big. And as you'll later know, LLVM is a major project that is used all throughout the software industry. Okay, so he's currently, and as of 2005, compiler architect at Apple. He joined Apple on the sole basis of LLVM, because Apple was looking for ways to optimize their tool chain, their compiler tool chain, and LLVM was probably the most innovative and best project out there. So again, his research turned into commercial work for Apple. So that's about Chris. Now LLVM, it's not an acronym, it's an actual name, although it used to be an acronym, but now it's the name for the project. And the project itself is an umbrella project. It envelops a lot of different parts in the developer tool chain, specifically compiler tool chain. It has debuggers, it has optimizers, it has internal representations, it has a lot of things. And let me start off explaining those things with an analogy to the way things were before. So what you see here is, let's say, the monolithic structure of compilers and the way they sort of currently are, and definitely were 100% before LLVM came over. So just imagine these circles represent different parts of the process. So it goes from parsing to sort of lexical analysis and all the way through down to machine code. And for any given language and any given target, you had this one big structure. If you wanted a new language, you had to sort of throw everything away, create a new structure, and populate it with these circles. So as you can probably imagine, that is not efficient. And if you had, say, M languages and N targets, you would need M times N compilers. So that is very inefficient in terms of efforts. Okay, now if you get rid of that structure, you can sort of transition over into this sort of scheme where you have a set of different components that you can re-engineer and sort of delegate to specific groups to work on. So that this allows, and this is what we've been taught in class, you have the source, the scanner, parsing, and this whole sequence is necessary, but if you break it up into parts, you can have different parts developed by different people, and if you're good at parsing, it doesn't mean you're good at optimization, and so people can then allocate their efforts to what they're best at. And since this is a very big sequence, I'll be focusing just on the two parts that LLVM is famous for. That is the IR, or intermediate representation, and the optimizer. Okay? So we can get rid of all the other parts. And start with the IR. So there are a couple of ways of going about IR, and the first one would be structured. So you can either have a graph or a tree-based system where you're taking your tokens and you're creating a graph from them. The other approach would be you can have a tuple-based system, which is flat, and you have a sequence of tuples that sort of usually collect 3 values, that is the opcode and the 2 operands, right? And then there's the stack-based structure, which is kind of similar to the tuple-based flat structure, but you sort of, instead of having a tuple of 3 values together, you would pop, say, X, you would push X, push Y, and then call the add operation. And it would pop these 2 together and it would add them, all right? So let's look at the LLVM IR. So what it is a low-level language that is kind of similar to assembly, and it is RISC-like. Do you know what RISC is in terms of CPU? So it's reduced instruction set, CPU, okay? It makes it more efficient. You can sort of break difficult commands and large complex commands into tinier commands, and then ideally they would execute faster, okay? And it is strongly typed, which is unusual. For an assembly language, usually they're just untyped, okay? This is a strongly typed language, so you cannot do assignment from an Intel float and that sort of thing. And like assembly, where you work with registers and like assign values to registers and pull values from registers, this works with registers as well, but it has an infinite set. So instead of AX, BX, whatever, it has 0 through whatever the number you want. Okay? Now let's go to the optimizer, and obviously from the previous charts it has 3 parts. It has the front end and the back end, but in the middle sits the optimizer. Now that's a very vague term, I guess, but hopefully by the end of this you'll get a good sense for what it means and what it is to optimize it. But so what the optimizer allows LLVM to do is, if you take a whole bunch of input languages or source languages, and you have a whole bunch of targets, right? You can, with the IR that LLVM provides, you can sort of translate each one of these languages over to that IR, and then translate that IR to any target you want, as long as there is a way to translate LLVM IR to a target. Okay? Now this allows for a lot of modularity, as you might guess. Now with whatever the number of targets you have for x86, PowerPC, ARM, whatever, and whatever the number of source languages that you have, you just need one optimizer, and you can link those 2 together. So you're decoupling the structure, and obviously that is a good thing for development efforts. Okay. So there are a couple of approaches that existed and currently exist. Take, for example, the Java and .NET. So this works in a way where you have your Java bytecode, and it then runs on the JVM, which is the Java virtual machine. And what this allows you to do is write your code, compile it into the bytecode that Java provides, and then run it on any JVM. This is good. This is part of what LLVM provides, but it limits you to a specific kind of structure, and that structure is the Java object model, which is bloated, shall we say. It has a lot of parts, and not every language is a good candidate to translate over to that sort of structure. You also have this approach where, since C is so ubiquitous and GCC is a very good compiler at what it needs to do, which is compile C and C++, a lot of languages take the approach of first taking their language, the source, and then compiling it into C. and then using that sort of intermediate representation, and then using GCC to compile that further to machine code. Examples of that would be Python. You can compile Python over to C and C over to machine code. And obviously you have GCC, which is very popular. It is probably one of the biggest, if not the biggest, open source compiler projects. It is a very old project at that as well, and a couple of things that come from that is you have a lot of structure that is mediocre. It's not ideal. So a lot of parts of GCC are outdated and bloated, and that kind of structure, and as well it's monolithic. So you have everything coupled together, and if you would like to write a front end to GCC, which is some sort of custom language, you'd have to rewrite the whole thing, or I don't know, parts of it, but very, very major parts. So that's inefficient. And LLVM IR takes care of all of that. Okay, so that's IR, taking your source language and parsing it over to some intermediate language, right? But that is still a language. Now, why do we do that? Would anyone care to guess? Why would you have source language parsed into some intermediate form? I don't see any hands opening up.
So I could break it down, that intermediate code into machine code better?
Yeah, but how better?
So that you can make a transfer like such in case, let's say you're executing some R code that you're doing instead of like repeatedly translate it multiple times, it just usually wants to be.
Exactly. Yeah. So with a representation like that, where it's assembly-like, modular, strictly typed, that sort of thing, you can then do analysis on that and get rid of redundancies. And I'll show you how they do it. So first of all, you look for a specific pattern that you know is redundant, right? You take your intermediate representation and search for patterns. Now, you take those patterns and you pass them on to objects that transform the pattern into something more efficient. And then you check whether it is a safe transformation. So by transforming, whether it will break the rest of the code or not. If you confirm that, then you execute and you complete the transformation. Okay? So this was an overview. I'll get into specifics for IR and how it looks like with an example. So let's say a typical C function, add 1, takes 2 arguments, A and B, and then returns the sum, right? Pretty simple. Now how this looks in LLVM IR. Right? This is the assembly-like language that I was talking about. You have pretty much the same structure, right? You have your function, you have your 2 arguments. The types are, again, strictly typed, so this is an integer that's 32-bit wide. And again, one of the things that is specific to this language is that it's the variables are not mutable. So once you assign something to a variable, you can't change that value. You have to create a new variable and assign whatever operation you want to that variable. So this is why you have this temp1, okay? You assign the sum, and then you return the sum. And the final bit about the LLVM IR is that it is transformable to 3 different forms, and at every point you can go back. So you start off with your text, the assembly-like language that I just showed you. That gets transformed into memory and data structures in the memory that the optimizer uses. And once that is done, you can save that into bit code and store that on the disk, okay? But if you want to, you can get back from bit code to the same assembly language and go around the loop again, okay? So at every point, these representations are are the same, sort of just different forms of the same thing. And you can get back sort of how Java bytecode, if you compile it, you can always look it up and see not the exact same names of the variables, but you can still see the same structure that you had before. So this same applies to LLVM IR. Okay, now I'll give you 3 examples of patterns that you can optimize. So let's start with the first one. How would you optimize this? Exactly, it's 0. How would you optimize this? Okay, and the last one? Boom. So this is kind of simple, but you get these types of things in your code, and these, in order to optimize your program, you need to get rid of these. So having this sense of patterns and ways to optimize them can move over to actual implementations. So if we find things in our code, in our intermediate code like this, you obviously get the sense that this is 0, right? You sub A from A, you get nothing. The exact same version of the second example and the third, right? So with these, you then sort of go to the optimizer and get to see the whole structure there. So the structure is pretty simple. You have your instruction, which is an object that delegates the optimizations based on whatever operation you were conducting. So that was subtraction. So this goes to subtraction, simplifier, and then you get the value at the end, okay? So let's begin with the first one. This is a for loop that iterates over all the blocks in your code. So just imagine line by line, okay? And this is the object that delegates, okay? So the delegator then picks, depending on the operation that you were conducting, in this case subtraction, over to another instance that takes care of common patterns and ways to optimize them. So these are the 3 patterns that would be there for the 3 optimizations that we discussed. You have your x minus 0 equals x, and this is C++, by the way. LLVM is written in C++. So this is just a method within a class, which is called simplify sub instance. And depending on the pattern, you return a specific value. Say in this case, if you subtract from whatever 0, you get that same thing. If you subtract A from A, you get nothing. And if you do this operation, you get X. So these are sort of the first part, the second part of your operation, the 2 operands. And then you get the value, which is the end result of your optimization. And it is replaced throughout your source, or the assembly is assembly-like intermediate representation with that optimization. And again, back to the same loop. This looks kind of simple, right? This is not complex at all, but this simple operation does a lot to the efficiency of your code. All right, so in summary, Chris Lattner, right? The guy that invented this thing. He's a compiler architect at Apple, been working there since 2005. He invented LLVM as part of a research project at a university. He designed Swift, and that's why I picked him from the myriad of options to give a presentation on, because I love Swift. Swift is my favorite language. And he's an awesome dude to have done all those things. LLVM, so it's a umbrella project that has a lot of tools in the compiler toolchain. 2 main parts. We've talked about the LLVM IR and the optimizer. So it has a modular design, and that is the main thing that allows it to be sort of used throughout the industry to work on specific parts of the compiler. And it has a unique intermediate representation, which I showed you, which is the most important part of the design of LLVM. It's a first-class RISC-like language that's strongly typed. And as I showed you in the 3 circle slide, it is an isomorphic form that goes to memory, to bitcode, and back without any problem. All right, so that's part where you have any questions, I can answer them. Everyone's floored. Okay, I guess that's it. Thank you.